Hello everyone and welcome to this last week of the second module. I hope you are enjoying it so far. This week we are going to destroy a car, and this is a very cool effect you are about to learn. As you can see, we have chosen a overly complicated geometry with this car, and this is uh, this is what we wanted, because as I told you the first week, we don't want you guys to learn how to apply these effects or how to learn it with using simple spheres or boxes, but the real geometry you can find either in a company or in some internet source. So I think I'm gonna have a bad time fixing this, but uh, I also think this is good for you, watching me struggling to fix this geometry, to clean it as much as possible. And the effect we want to achieve is to throw some props, some street light to this car. We also have them here, and we also will have to optimize this geometry. But I think this will be much easier than optimize this car. And before starting, we should learn how to create some denting effect with using either hard and soft constraints. So I have prepared for you guys a simple demo scene here, and let's go to it. The first thing I want to show you guys is that we are using exactly the same geometry from the beginning to the end. And this is the goal of this effect, because we don't want to change the geometry of the car. We want to apply the effect on the same geometry incoming. So let me quickly show you how to do this. No, first I want to show you the final effect. I'm just throwing some balls to this grid, and I want to achieve some metal denting effect. So this is the result. And to achieve this, let's first take a look at this grid. We had to add some resolution to it, because we want to have some geometry like the car we have. And then the next step is to create unique points. And by doing so, we are separating each primitive from the closer one. So we can add some operations to each one of these primitive. As you can see, if I middle click this grid, I have 2,500 points, and then using this creating a unique points operation here, I will have 9,000. This is because we are creating unique points for each one of these primitive. I don't know if I'm going to use this method on the car, but it's cool that you know that exists. So then I can use this primitive sub to apply a scale to each one of these primitives. So I only have to turn on this do transformation option and then scale down, for example, to 0.8. Now, next step is to give to this geometry some thickness. So I will extrude this. Of course, we have to turn on the output back and then assemble it to pieces. You have to imagine this as the fracture we have to apply to the car. So I will end these pieces by giving them, of course, a packed geometry, because we want to use a bullet solver, and therefore we need RBD packed objects. And then what this wrangle is doing, as you know, is setting the pieces below some distance to a 0 value of the active. Okay, so this is regarding the pieces. And then we have to create a constraint. So what I'm doing here is using a simple connect adjacent pieces. But let me template this example, because I think this is interesting. If I set this to 1 maximum connection, I am only connecting these points to the one upwards or below each one of these pieces. Uh, to have a more reliable and realistic effect, I have to connect it to the one on the left and the one on the right. So let's just pump up the maximum connections to, and now we have something like this, which is more reliable. Okay, so the trick and the core of this car simulation comes now. So in previous versions of Houdini, we have to set this manually, and this is what you are seeing here, this script, before these next statements. This is something that you already know. We are just setting a constraint name, a constraint type to all of these pieces, but internally, we could use the next constraint name, which is an attribute that comes along with the constraint network creation, and the bullet solver can recognize. And what this does is to change the constraint once this is broken. So what the constraint network is gonna look for is the next constraint name, and this means that when this first constraint is broken, set this constraint between these pieces to another one, for example, a one called sub. And we are going to use another constraint relationship. But with Houdini 17, we have this much convenient workflow that it comes with the RBD constraint properties node. And if I turn on this switch constraint type when broken, as you can see, we can do exactly the same. And this is intended to switch from glue to soft constraints. But we can switch to glue from whatever constraint we want. But if we switch to soft constraints, we can also override and create custom parameters to custom values to these parameters, like the stiffness, damping ratio, constraint intonation. I will show you this in a bit. So I will start with the first one. I just simply want to get the next constraint name and the next constraint. And I will start by using a hard constraint once the glue is broken. So let me change this to hard. And this will be the end of the constraint relationships. This network, this top network I have here is the simulation I just showed you, so I don't need it anymore. I'm gonna work with this one because I have everything by default. And here we have a sphere, and I will create a setup to emit these spheres within a range of time. But we are not getting into it because we just want to learn how to create a constraint. So this setup I say is this mission sum network. I can control the emitting frames and the scale of the sphere, but what we are really interested to learn is the constraint setup. So as you can see, I have the wall. Here I'm showing you the wall with the guide geometry representation. Actually, we should override the active value because, as you remember, I had set to 0 all these pieces here. Then I set this to convex set of connected primitives, the collision padding to 0. And then we have called the constraints. So I set this constraint network to the second context geometry. And as you can see, we are watching the first set of constraints, which is the glue constraints. And the method and the workflow is to merge the first and the next one. So the first constraint is going to be the glue constraints with these values by default, and the second one, once this is broken, it's going to automatically switch to the hard constraints. So also I have a ground plane here, but I'm not showing you. So let's give it a try to the simulation, see what we got. There you go. Of course, I have changed the name, so I have to change the name here. Let's say this is hard. Let's do it again. And let me go frame by frame, as usual, to show you what's happening here. As you can see, these new constraints of type glue hard are being created every time these glue constraints are being removed. So the first step is working fine. Now we just have to tweak these parameters to get a proper effect. So let's first, as usual, set this suppress length to 0, the error reduction to 0. Let's see what we get now. Okay, let me watch this side view. All right, you can see we're starting getting some denting effect out of this. Let me see if this is by default. Yeah, this is all by default. So how we can get more control of this? If you tweak the strength, for example, I'm gonna set this 1000 times stronger, this is not gonna break. So let me try this value. This is breaking easily, and you can change the propagation rate to affect the neighbors of these polylines, of these constraints. So I don't want this, so I'm gonna set this propagation rate to a low value. Let's see. Okay. Next thing you can tweak is the number of substeps. But be careful with this, because this is gonna affect either the constraint behavior and the way you have the collisions. If you have a very low number of steps, for example 1, 2, 3, maybe these spheres are gonna go through this this wall, because they are not gonna detect the wall from one substep to another. Let me show you quickly the difference between having these 4 substeps. Okay, let me now set this to 50. As you can see, we are having much less denting effect. Let me quickly size down this radius. Okay, and the other thing you should tweak is let me set this by default, is the constraint iterations. This is how hard the constraints are trying to settle down in each substep. So if I set this to a very low value, we are gonna get something that keeps moving and keeps trying to get a still position in each frame. And this will be unrealistic, as you can see. You can see these pieces still moving. This could be cool in another effect, but not to this one. So let me change this, for example, to 50. And of course, this is going to be way slower, but I think we're going to get exactly what we want. Let me take a closer look to it. Also, we can change the number of steps. There you go. You can see these pieces aren't moving. And we can also change the sleeping time. Let me set this to 0.05. And there you go. This new position will still static until some other ball impacts to it. Lastly, we can tweak the scale of the spheres, and we could also tweak the mass, but since these spheres are sharing the same density with this wall, this is not going to be a effect. So let me show you what happens if I pump up this scale to 0.8, for example. Okay, I think this is good enough to show you the next step. So let me change this hard constraint relationship to the bullet soft constraint relationship. You can call it by typing soft bullet, and is this one. Now if I plug this to the second input, nothing's going to happen because this doesn't have the same name, and it's not going to fit to this method. So let's set this to hard, and let's set this to by default values. Let's see now. Okay, this should be fixed if I change the rest length. Let me see. As you can see, we are having kind of the same effect as we have with the hard constraint, but we also have a damping ratio and a stiffness. But as you can imagine, having more control and more parameters to it, it will make these simulations lower. So we could achieve the same effect and the same outcome using the bullet soft constraint, but the hard constraints are faster and more reliable. You can see the damping here. I will let you play with this. I don't have so much time, and let's just connect the spring constraint relationship. Let's set it by default again. See what happens. Oh, of course, I have to change the name. Let me see. There you go. This is exploding as expected because we have to change the rest length. Okay. Let me see. Let me lower down the radius and set this to high value, this as well. Let me set the rest length to 0. And this effect will behave like a spring, which is, I think, is not the perfect or the optimal geometry to apply this effect to, because I think this will create kind of a fake and bad ripple effect. Let me set this to higher values. Maybe let me want this effect to be more clear. So let me see now. Okay. Maybe less, even less. Maybe if I scale this up. Whoa, this is exploding. Yeah, this is always exploding. So, as I said, it's not the perfect situation to apply this effect, so I will leave it to you to use it. For now, let's just go back to the old scale and using the hard constraints. Let me see if I still have what I had. Okay. Let me give it some more frames until, yeah, something like this. And I'm gonna jump back. And what I'm doing here is importing the simulation uh, blasting the ball. I don't need them. And the node I have to use now to transfer this deformation to the original geometry is called point deform. So I have to plug into the third and the second input the simulated geometry. In the third one, we have to plug the deformed point lattice, which is this one. In the second one, we need to plug the rest point lattice, which is this geometry, this simulation at the first frame. And in the first one, we have to plug the mesh to deform. So if I display this, you can see we are getting this mesh to deform. How we can achieve the cool and realistic denting effect similar that the cars have when they crash? We can maybe use a remesh node. So we can have these sharpened edges will help us to get and to achieve this crash effect. But as I told you, we are not we're not gonna save this geometry. We want to apply this method to the first geometry. So we have to use another point deform. And by the way, you can tweak these parameters to see the difference. So if I use another point deform, this time aiming to the first geometry, we are getting this deformation with these sharp edges to the first geometry. And then I just mix it with the balls, and there you go. Where are the balls? Let me see. Oh, here. Okay. There you go. Cool. So now we are ready to start with the car destruction. Now, as always, you should start by importing the geometry we have to work with, and also we have to save this scene. So what I've done is saving this as module 2 week await folder, and I name it as week await denting Mercedes, because we are about to destroy a Mercedes and the version. So let's save this, and I'm gonna create a geometry node, and with this file you have to call this geometry. You should have, I place it in the cars folder, and now the first step is to clean the geometry, fix the scale, fix the groups if we have to, and maybe add some rest attributes to apply the textures. So let's start by transforming this. I'm gonna add the transfer node, and actually I want all these cleaning operations to be placed inside a subnetwork. So let's create a subnetwork, call it clean. Let's add inside, and of course this is too big to work with. You can see it at simple glance, but how to scale it properly? We can use again the Tommy geometry. So let's say, for example, 0001. Let's frame this, and if I display the Tommy geometry and I display this car, let me go to the from view. I think we are lucky, and it looks like the scale is pretty much done. So I'm gonna leave it like this. Now let's say goodbye to Tommy, and we can continue by deleting the attributes we don't need. So let's start with the point attributes. Let me see. It looks like we don't have any point attribute to get rid of. We have the material path, which is gonna help us to go from one group to another. but we also have the groups, so this geometry is good enough to play with. So we can just hook on a rest position node here, and this rest node is gonna be transferred through all the operations for texturing purposes. And now we could start splitting this geometry. I will need 3 parts. The first one is the part I would like to bend to apply the denting effect. The second part will be the static pieces of this car, which they are not going to move, or maybe they are going to move as an animated static object. And the third part will be the windows, because we want to apply some different simulation there. So let's press S and 9. As you can see, we are getting the parts. I think this by connectivity. So let's just change to groups, and I'm gonna press Shift and select all the groups I'm interested on. Something like this. This will be the parts of the car we are going to deform. These two. I'm just pressing Shift and selecting everything I think should be deformed. Okay, these two, and this as well, and this, and this. Okay. Okay, let's press delete. Maybe this, yeah. Press delete. It looks like I lost my selection. So, oh, okay, here it is. Now, all right. So I'm gonna delete not selected all these parts, and I'm gonna duplicate these and turn off the non-selected, because I want to select the glass geometry out of this. So let's go again and select this, and this is also glass. Let's see, and this as well. Okay. Okay. Gonna press delete again, and this will be our glass. So now we have to again duplicate this glass selection and apply it to the static objects, but this time turning off the non-selected because we don't want the glass here. And we can also get rid of more elements here, so I will just press S again and select all of this, this. If I made a selection that I don't want, I can control and drag the mouse to deselect it. Okay. Okay, let's add this to the body. So I can just duplicate this blast, set to non-selected, and merge it to the body, like this. And now remember that we can output things here. Let's set this to the first output, adding an output node here. Then this will be, I think I forgot to, yeah, I want these pieces. Okay, so let's merge them as well here. Okay, so now let's output the static geometry here. It will be this one. And also let's output the glass. Okay, so we can call a null here, and let's name this as body. Maybe I'm gonna switch the outputs. This will be the body, but I want this to be the glass, and I want this to be the static. So let's organize this by pressing L. Let me see. Okay, this is glass, and this is the static. Cool, so let's start by doing the easier step, which is fracturing the glass. So I'm gonna do it inside a subnetwork as well. And so let's create a null node, create a subnetwork out of it, and dive inside. And here, since I need the reference, and this is a good trick to know, we can import images to the network by pressing Shift-I, and then if I choose, for example, this image, I can place it wherever I want. I can scale it, and I can play with the brightness. And once I'm happy, I can press Ctrl-I, and I can no longer edit this until I press again Ctrl-I. So the fracture pattern we want to achieve to this geometry, to this glass geometry, is actually very easy because this looks super close to the Voronoi cells pattern. So let's simply add a Voronoi fracture here and a scatter node. And as you can see, we don't have a thickness on this geometry, so I will apply it without using an inside faces, interior faces. So let's just connect this here. Let's see what we get. We can start by simulating and playing with few pieces and then pump up the resolution, because as you could see in the image, these pieces are super small. Actually, I'm gonna break this operation, because before computing the Voronoi fracture, I have to set off the create interior surfaces option. So let's set this to manual. Just 1 second. Okay, let's set this to manual, and then check this toggle off. Maybe I can lower this to 500, and this time I don't want to turn out the relaxed iterations, because as you could see, this pattern is uniform. Let's see what we get. Okay, of course the cells are super big, but we are starting, so maybe later on we will improve it. Let's now, it's a good idea because we want to throw a street light to this car. The effect will be like a piece of geometry falling down, and it will be nice if I can set the initial velocity to these pieces, because otherwise it will fall down with the gravity. So let's do it by using another cool technique, which is transforming this. Let's center the pivot, and I want to template this. I'm going to add some uniform scale, and what I'm going to do is to compute the vector, compute the subtracted vector, the point one to another, and then I will get the vector direction. So let's do it by using a wrangle node here, and we have to assemble this first. So let's do it by using an assemble, because I want to set this velocity to the packed pieces. So let's create packed geometry. We already have a name attribute, and then connect the second input to this transform. And I need to do a subtraction operation. So first I have to ask for this points position. So let's do it by creating a temporary vector variable called, for example, p2 of position 2. And let's say this is point 1 of the second input. We want the attribute position for each point number. And now the velocity vector will be a normalized vector between this subtraction. Now if I control middle click this, I should be able to watch this vector visualization. Sometimes it's not working, so we can add an add node here, and we can keep the points. And of course, this has to be plugged into the assemble, and there you go. Now we can end this by creating an attribute randomize, because I would like these pieces to have a velocity direction pointing more to the ground. So let's set this to velocity. I want to add some values, and let's play with these minimum maximum values. I don't want to tweak the x and z direction, but just the minimum and maximum. So I want something like this. Cool. So let's just create an output here, because remember we are inside a subnetwork, and let's call this glass. It's computing again the Voronoi. I don't know why, but you have to wait. And what I have here is our geo class. There you go. Let me take a look. Okay. Perfect. Okay, so time to play with this body, but before doing it, let's maybe create a checkpoint by caching this simulation, this fracturing, sorry, because otherwise, if I open again the scene, I will have to wait until this fracture is done. We don't want this, so let's use our custom file cache. I already have it in the clipboard, so I'm going to paste it. You can go to the previous week to get it, and this will be, for example, geometry, glass. Yeah, and this is type geo glass fracture over 1, and this is a current frame. So save it to this, load it, and here we go. Don't worry about the static parts. This is fine for now. We are only going to use it to make a static object out of it. So we can start with the body. So let's make some space here. And as you can see, we have a lot of information here. We have a lot of polygons, and the effect we want to apply to this body is not fast effect. We have to create a lot of constraints. So I think the best choice would be to start with using a simple representation of this whole geometry, which could be, for example, if I go to the groups. This is groups. Yeah. So I could take, for example, let me go to the material palette. Let me see. Yeah, maybe I can start with, no, maybe the groups better. So I want to take the groups. I'm going to grab these, and these, and these, and this. And I want to set this to non-selected. And we can start with this simple geometry. And remember that we want to apply the denting effect to it, and then with using a point deform, we will transfer the deforming to the original geometry, which is this one. So we should reduce this geometry. But before doing it, and since we have to Voronoi fracture this, let's make sure this is a this geometry has some thickness, and we can use a BDB from polygons. And if this creates a good representation of this geometry, it will mean that this doesn't have any open polygons. So as you can see, we have to fix this geometry first. So let's just apply a polyextrude node here and output back and give it some interior distance, something like this maybe. And let me see what we get from the BDB. I think this resolution was too high, so let's set this to 0.005. Let's see what we get now. And there we go. Okay. Cool. Now this is fixed, but we, as I told you, we should play with less polygons. So we can maybe use a poly reduce node. Set to, for example, let me set this here, and I want this to be 15%. Okay. It looks like we are not losing the hard edges, so there's no need to set a hard edge group here. So now it's time to fracture this geometry by using Voronoi fracture and a scatter. Let's plug it here. Or maybe we can set this to fuck BTB to have points within the geometry. And of course, we don't need many points. We don't need 1000, but let's try 50. And set this to the first input, this to the second, wait until this is done, and let me see. Okay, so all of these edges you see here is the region where we can have some deforming effect. And as you can imagine, you can customize this deforming by adding more noise, by changing the scatter, by changing the area where you want to fracture this. But for the sake of speed, I'm going to leave it as it is. So let's explode build this to see what we got. Okay, and maybe I can add a color node here. I don't need to visualize this. Let's paint this as, for example, this color. And in one hand, we should start creating our tag geometry to send to the DOP network. It's going to be this. Let's call this in-sim body. And then, on the other hand, we have to start creating the constraints. So I need first to create constraints within all of these pieces, and lastly, I have to constrain this geometry to the static object. But expect some errors here because we have just a part of it, but it should work good enough to see if we are achieving our effect or not. So let's grab, let's first merge this with the static object. I don't want the lines to be cross my network, so I'm gonna call my static by using an object merge here. And this needs a name attribute, so let's create an assemble node without packing because we are creating constraints. Maybe give a color to this. For example, this blue. Okay, and now we can use our connect adjacent pieces. Okay, so let me check these connections. As you can see, I would like to have more connections because since we have deleted a whole bunch of pieces here for the sake of the speed, we are missing a lot of polylines. So we can maybe add more radius to this and add more connections. Yeah, I think this should work. So I'm going to show you a new method you can follow, which if you remember when we have to select and split all of these polylines depending on their point colors, we have to use a for each combined loop, which I told you was pretty fast, but even using that method, we can use another one way more faster. So I leave it to you to choose between one or another, but right now I'm gonna use the other method, which is a little bit more advanced, but it's if you learn it, it will worth it because it's just 4 lines of code. So let's drop down actually a primitive wrangle node, and I'm gonna do the following. I'm gonna create an array. Array is I think it's called dictionary in Python, but it's something where you're gonna store variables. So I want an array for each one of these primitives, and I want to save the point number, and then I want to get the color of this point number, compare it, and remove it if the color is the same. And doing it by using an expression or a script here will be much faster than using a for each loop node. So the first thing I have to create is an array, which is going to be an integer array because we are getting the point numbers, and I'm going to call it prim points. If I add these brackets at the end of the this variable, this temporary variable, this wrangle will understand I'm creating an array. So let's use the function prim point. Remember, you can see the information of this function by clicking here and taking a look at the Houdini documentation, pressing F1. And this needs the input geometry and then the prim number. So I would say the input geometry is 0 as always, and the prim number is prim number. Let me see what we get from here. And to cast an array to a geometry spreadsheet, I have to write it like this way: I brackets and then add prim points equals to prim points. And there you go. We have for each one of this primitive the first and the second number, point number. If this were for a polygon, we will have 4 points, a square polygon. So let's comment this, and I want to call the color that this for each one of these points inside the array. So I had to create a temporary color vector. This will be the color for the point 0, and I'm gonna say take the point coming from the input. I need the color attribute, and I want to get the first value of this array. And the arrays, as the point number goes from 0 to the maximum number you have here. So this will be the value 0, the value 1, comma, value 2, 3, 4. So I have to get the 0 value of this array. So I have to type prim points 0. And then I do the same with the other color. Let's create an attribute for this, a vector attribute, 0, equals cd0, cd1, and there you go, cd0 and color 1. And let's finish by creating a condition. If the first color equals to the second one, as we did with the for each loop method, remove all this primitive and the point number. And there you go. This is way faster than the other method, as you can see. Okay, now let's create the adjacent pieces, the constraints for the body of this this car using this in-sim body. So I will just plug this into this geometry, and remember this has to be unpacked, so I'm gonna plug it here instead. And maybe change these values to by default. Let me see. I'm gonna set the rest length just in case. Cool. Now I'm gonna use the now RBD constraint properties, and this will be the constraint car, and same with this will be the constraint mix. Okay, so now I want these constraints to switch not to the soft constraints but to the hard ones. So I can type this here, hard, and same with this one. So let's set this to hard as well, and maybe the mixed ones will be, we should pump up this value. I want them to be hard to break. So now we can merge this. And we can end by calling a null and say this is the constraints. Now I think we have the simulation body. Is this, yeah, packed fragments. We have the constraints as well with the name. We should get rid of these attributes because we are not gonna use them. So color, rest, yeah, let's leave this for now, and maybe, let me see, all of these groups, because we are we don't need the groups on the constraints, so let's delete them. And I think we're ready to start our simulation. Let me see the static object. Okay, let's set this to pack geometry. So I'm gonna create an assemble node. No, actually, I think I have the static object here. Okay, and yeah, let's create another assemble node, but this time I'm gonna pack this geometry. Okay, and set this to static, or maybe in sim static. Great, so now we can see we have the static object, we have the constraints, and we also have the trimmed part of the car that we are gonna use as first example to dent. And now we need something to throw to this car. So I think it's a good idea to take one of our props, for example the street light, and make it fall down. So what I'm gonna do is to object merge our props. Let's go to the props, and I'm gonna take this out that you don't have already, but I'm gonna show you what I've done here. So the idea is to make this street light fall onto the car, but before you have to optimize this street light. So let's take a look what I've done. First, we have to call our street props that I had in the props folder inside the geo folder. Then we have to scale down. We can use the car as reference. I think if I have the car here, let me, Yes, here the clean version of the car. This is the size I'm using. So I think it's 0.15, which I found is a good size. And then, as always, delete all the useless attributes. And here, what I thought is to throw or to make only the street light to fall down. So I get rid of the other prop, and now I have to set it on the correct position, like here. And also, if you can see here, I don't know why I have 2 spare points that I have to delete. So this is what I've done. And then I move it again, just to make it fall onto the car using the centroid. As you can see, I made this pivot to be on the base of this street light by using the centroid function on the X and Y pivot parameter, but the B box and the minimum value of the B box to the Y component. And this is the same as we have here. This one. Sorry, this one. So I move it and I rotate it a little bit. And then, of course, we have to use the convex decomposition to clean a little bit our geometry, make it bullet solver friendly. And then what I did is to pick this little bit. Pick is a node that increases or makes the geometry grow towards the normal distance. And then what I've done is to first assemble this. Take a look that we are using the prop name, and I noticed that this is splitting the street light into 5 parts, but this is not what I want, because if I make this fall down, all these parts are gonna split. They're not gonna be together when they are inside a bullet solver. So we can either create constraints to it, but I think it's much more easier if I just pack this again, transferring all the attributes. So now I only have one pack geometry. So this is what I call from this node, this object merge, and then I can create a null here and call this as in_sim_props. Okay, time to create our .network. I'm gonna do it inside this node this time, but you can place it wherever you want. Let's call it sim, dive inside. Actually, let's call it sim car, because later on I will have another .network with the class. So first, what I need is, as usual, the rigid body solver, gravity, and ground plane. So let's connect all of this with a merge. All right, now the RBB packed object. And we could start by calling the static object, but I already know that I'm going to use a merge. So let's say static to this one. And I need a subpath, so let's jump up 2 levels and let's write in. And here I have the static object. Okay, this is the display geometry, but I need to take a look at the convex hull representation of this. So, as usual, we have to convert per set of connected primitives. Maybe we can change the collision padding. All right. And this will be a static object. Okay, now let's call the car with another RBD packed object. I'm gonna plug it here. And this is an active object. And we can easily call it using, the in sim body, because it's the body of the car. There you go. Let's again turn this on. Take a look at the guide geometry. Maybe I can change the color. Let me see. Lower the collision padding. And that should be it. So now let's call the props, the street light, and as well you can use the in prefix here and use this one, which is also an active object. So now let's take a look at the geometry. Of course, we have to create combat school here. There you go. I think all the geometry representation is fine, so let's grab all of them and turn off these guys and display the geometry. And we could start creating the constraints. Let me organize this by pressing L. But maybe we can take a look if this is running well. Let me lower the sub steps. I expect this to be fast enough. So let's take a look. Yeah, I think it's good. It's a good start. So now let's call a constraint network. After the rigid solver, maybe constraint network. And actually, I think I merge all the networks here in this constraint node. But what I'm gonna do in order to have more control in each one of them is to split this operation. So first, I'm gonna call the, let's see, I'm gonna call the car constraints. Let's merge glue and a hard constraint here. And this goes to the second input. Let's call this constraints car. And then let's do the same. But this time, I'm going to start by only using a glue constraints because I don't want these constraints to be bending. So let's call the car the constraints mix, and here mix as well. Okay, so let me see. We have to change the name, of course, as glue and glue. Let's change the color to this one, and hard constraints to hard. You're not watching the hard constraints because we have to wait until the glue constraints are broken. So let me double check this is the proper name by going to the car constraints and taking a look at the next constraint name, which is hard. Perfect. Let me see this. Yeah, I don't want to switch constraints, so I'm gonna turn off this. And with all the options by default, let's give it a try. I'm gonna press play. See, something's happening here. Let me see. It's weird. Let me create a new viewport. Okay, it looks like the constraints are being created. Maybe let's pump up this value. No, they're still falling. So there must be something wrong with the naming. Okay, let's take a look at this. We have the static object here, and we are assembling this with a name. So we have a name here, which is piece, and I think I'm gonna change this piece name to static, because maybe this is overriding the body name, which is piece. Yeah. So let's instead change this to a car. Actually, I'm not creating the name here, but in the board manufacturer. So let's call this car, and now I have this name of car, static, and car here. Have you seen how fast is this wrangle going? And car and static here. So it should be it. Let's give it another try. There you go. Okay, so far so good. This is not breaking, so let's start by breaking these car constraints and see if we are getting the hard constraints once they are broken. Okay, let's maybe lower this radius. And we can start tweaking all the by default parameters we surely know that we have to tweak, like this one and this one. We can set it to 0. I'm gonna color this. These are the mix, and those are the car constraints. Okay. Let's hit play again. Okay, we can start seeing some deforming here, but I need more. Maybe we can change the, let's call this prop. Maybe we can start tweaking the physical parameters of this. So let's start by changing the density of the prop, maybe 100 times the old value. Let's see now. Okay, looks like this is affecting. Cool. Maybe we can lower the bounds. And actually, I'm gonna set this to 5 times harder. Let's see now. Okay. Or maybe we can even give it a velocity. I don't want to spend many times here, so I want just to get some quick result. Oh, too much. But as you can see, we are changing the way these constraints are behaving. Still too much. Maybe set this to 10,000 only. Yeah. Yeah, I kind of like this, so let's see what more we can improve. I'm gonna go frame by frame, and first thing I noticed is this is that we need a still outcome of this, and it looks like it's never stopping. So if you remember the first part of this week, I'm pretty sure that what we have to tweak is the number of substeps and the constraint iterations. So let's first tweak the constraint iterations, because the number of substeps makes this geometry to bend and to have this denting effect more easy. And if I pump up this value, the simulation is gonna go way slower. So let's start by setting 10 times this value. Okay, as you can see, because the constraints are going to this to the rest position faster, the props, the street light is adapting to this new geometry. So maybe we can set a middle symbol, something in the middle. I mean, we can maybe set this to 10 at the beginning and 5 this at the beginning, and then when this is colliding to the object, pump it up to make it stop. Also, we can change the sleeping time to something very low, and I want to see this deactivated color of the street light, so I'm gonna turn this on. And let's see, now I'm gonna search for some frame to animate these values, maybe frame 9, and I'm gonna set this to manual. And let's say, I don't know, maybe this will be 150 and this will be 15, for example. Yeah, let's try this. I think we are fine with the other options. So let's try this again. And I'm going to take a look at the animations. Actually, I don't want this to be growing, so I just pressed B. And this is the constraint iteration, so let's set this curve. I want this to happen all of a sudden, and same with the sub steps. Something like this. Yeah, let's try now. Maybe let's set this frame earlier, maybe 3 frames earlier, something like this. And I will set this to 30. This looks like still bouncing. Friction. Maybe I can lower down the rotational stiffness and lower this down as well. Maybe start with 20. Let me see now. All right, this is too much, so let's set this to 0.05. Yeah, I think I like this. So let's keep going because I don't want to waste more time on this. So let's jump back, and as always, you have to import this. And since I'm doing this in this this operation on the car network, I will just use the import of the operator input 0, taking the car, and I'm gonna pause the video and I'm gonna save these as create points to represent objects. Then with the transform pieces, we can transfer this attribute transformation to the original pieces. Okay, this is done. So as usual, I used my custom file cache to save these points, and doing it by this way is only whoa, this is super low, not even 1 megabyte. So I transfer these attributes to the in-scene body, and since they have the same name, the transfer pieces is working fine. And I know it looks weird, but this is exactly what we need. Now we have to call the this one to transfer to start transferring the deformation. So I'm gonna call this maybe how's it this called body. So let's call it body reduced, and let's paste it here. Body reduced, and then what I need is to first unpack this, and I'm gonna use a point deform node. So let's set this mesh to deform. As you can see, this is already unpacked. We need a rest point, so let's set this to the first frame, connect it here, and the deforming lattice. Cool, let's see what we get. And there you go. We could even change the shape of this first mesh to be deformed, because we want to transfer this mesh to the original mesh, but we want to keep the shape, the sharpened edges of it. So maybe we can, I'm gonna do this quickly, but I would try to reduce this to 30%, for example. Let's see what we get now. Of course, you can play with the radius to have more smoother geometry, something like this. And then we have to, again, point deform, but this time the original body. So let's call it, and maybe this will work. Let me take a look. Let me call this body. As I said, I'm using all this object merge because I want to avoid having all of these fulfilled with lines. So let's connect this to the mesh to deform. Is unpacked. Let's maybe copy and paste this timeshift here to the rest point. Now the rest point is the output of this point deform, and the third input is this point deform. Alright, so let's take a look now, and there you have the main geometry. This is looking super weird because we are only deforming the reduced body, not the whole one. So maybe we can just copy and paste this blast now, and there you go. Let's maybe play with this. Let me see. In order to maintain the original shape, the sharpened edges. Yeah. But as you can see, this is the first step. I will let you play with this because we have to keep moving. Let's add this as car body deform. And I'm going to maximize this window because I want to add network boxes to each one of these. Not the out, but not the in, but the out. For example, yeah, the static one. And the props. No, but the props. What I want to do is to import our street light. Let me set this to operator input 0, and I think I call it prop. There you go. You may want to cache this as well. Let's call it out prop sim and set another network box. So now I can easily find our outcomes and we can footprint them. No, this one. Okay. So this is what we have so far. At this stage, you are surely wondering where the windows, where the glass. So what we are gonna do here is to use a very cool and fast technique to add this glass after this simulation, because right now it's not very slow, but remember we trimmed the car and we are simulating with maybe 10% of the total geometry. Then if we add the glass, every one of these little pieces to the simulation, this could be a hell to simulate. So the trick is to get this glass, deform it, and using this deformation, we can activate these particles. So let's get to it first by importing our glass. I think it was called, let me see, GeoGlass, maybe. Let me see. Yes, this is the one I like, the fracture one. And remember, we have huge cells here, but later on we are gonna add more resolution to it. So first thing we need is to point deform this by using our simulation. Don't need to use the whole mesh, but this one will be fine. So let's time shift this, because this will be the second input of our point deform. This is the mesh I want to deform, the rest point, and I did this by alt clicking here, and now I can split this line and connect it here. So now we have this point deform. Remember, we have to unpack this. And let's play a little bit with these parameters. Surely I'm gonna need more points here and here, maybe more radius. Yeah, this should be fine. I'm gonna leave it at 0.5. Now let's go and assemble this. I don't know if we have already a name. It's called piece, so maybe I can rename this as glass. Yeah, let me rename this. Should be here. Let's set this to glass and file cache this again. Is this done? Yeah, that was super quick. So let's go back here, and now I should have proper name. So don't override it, just create pack geometry, and there you go. Cool. So I'm gonna drop down an attribute wrangle node here. And the method that I'm going to use to activate these particles is to, compare the original geometry, which is this one, and the deformed one, and if the distance between them is higher than some value, I'm going to activate that pieces. Otherwise, they will keep in a deforming status. Remember that in this case, we need to play with the, with the active and deforming parameters here. I don't need the animated because these pieces or this body is not doesn't have a transformation on it, but just a deformation of these pieces. So let's drop down this wrangle. I will add the active attribute to these pieces, the ones that are deforming, and the second input should be plugged here. before the unpack. Now first let's grab this the position of the second pieces. We're using temporary variable vector p2 point 1 position ptnum, and let's start by setting this active value to 0, the deforming value to 1, because this is the first status of this geometry. Then I have to store the difference between the two vectors. So I'm gonna use I'm gonna call this float variable as diff of difference, and I'm gonna use the length function to get the distance between them. And then I will say if this distance is bigger than some custom value, custom channel, then I have to do a couple of things. When we are using brackets, it means that we are gonna set more than one condition. Otherwise, we can just write whatever here, and this is gonna work as well. But when we have to set two conditions or two statements, we need to add the bracket. So let's say when this is bigger than this difference, I want the deforming to be 0 and the active to be 1. Cool. So let's set this difference to low value, for example 0, 0.5, and now I would like to watch if this is working. So let's delete this by active points, and as expected at the first frame we still have all the pieces, but when they are being deformed, the pieces are being deleted. And as you can imagine, this should be a persistent operation, because otherwise these pieces could turn to deforming to active, and they will, or the other way around, and they will be floating on the air. So we need a solver here. Let's drop down a solver, type inside, and I only need the previous frame and the input one, because the input one is what is coming from here. So we got a wrangle node. I'm gonna overwrite the active value to the one I have on the previous frame. So let's say if point of the first input called active ptnum equals 1, then active must be 1. Perfect. Let's play this. And now we know for sure that if those pieces are having a value of 1 on the active attribute, it will be persistent. We can maybe take a look at the number of pieces here. We have 1,237, and maybe this will be different. Yeah, not big difference, but using this, you will be sure that things are done in the correct way. Okay, now that should be enough for a common tutorial, but we are not a common school. We want to go one step further. So let me see. Let me show you this. No, not this, but yeah, the deforming version of the car. As you can see, all the pieces that are being deleted are the ones that are gonna jump out of the car. But it will be super nice if we get some of these pieces still attached to the edge of the deforming body. So let's create an attribute transfer here, and I'm gonna call this point deform. I want to source something from this geometry to the glass and transfer some attribute to it. So this attribute, it would be clever if we call it deforming equals 1, and then we transfer this to the outcome of this wrangle. Let me show you what could happen. This is I want to transfer the deforming and I want to look at it. So no, we have packed primitives, so let's just use a blast node to watch this deforming attribute. I'm gonna set this to deforming and maybe lower this. Right now everything is deforming, but let's give it some frames. Okay, so this is the first thing we got, and right now you are watching the result with this attribute transfer. So let's set this to 0.5. Let me, yeah. Okay, so maybe the lead not selected, and as you can see, thanks to this attribute transfer, we are keeping these pieces near to the edge of the body, and this is cool because this is a realistic effect. So let's play a little bit more with this. Also, when of course, when we have more pieces on this will be nicer, but you can easily compare the two outcomes. And as you can see, we are saving these pieces here. Now again, we have to make this change persistent, so let's add a solver to it. And this time we want to override the deforming attribute by itself. So let's check this. Okay, let's go back. And this is not done yet. We have now to override the active attribute with this deforming. I mean, when this deforming attribute is 1, the active attribute should be 0. So let's create an attribute wrangle. Let's connect it like this, and I'll say active equals to 0.1 active ptnum. Now I'm taking the active attribute from the solver where we are setting the persistent active attribute, and then I want to multiply this by 1 minus deforming, because I want this active attribute to override everything but the deforming one. Let's set this integer. Okay. Now it's time to check this wrangle. We can give it some frames here, something like this. And we can either check the active and the deforming. So this is the active one. Let me see. Maybe we have to lower this a little bit. It should be working. Points, active. We have the same number of points here. Deforming. This is always 1, so maybe the problem is here. Let me see. Okay, guys, I paused the video. Sorry for that. I made a little mistake here. As you can see, here we are transferring the deforming to this geometry, but we don't want this deforming to override the active, because this will make the pieces stop, and what we want is to only the active attribute to be persistent. So it's as simple as deleting this solver and using the other one. So let's just duplicate this solver to make the active persistent, and then we can use this wrangle now. And if I set the display to this active here, you can see we are getting exactly what we were looking for. Pieces breaking, but this time we are keeping the edge of this simulation. So you can tweak this connection to see the difference, and I think eventually this will be much better. Perfect. So now after sending this to the top network, take a look that we have the proper attributes here. We'll override the RVD packed object by attributes by these ones. And I'm missing some velocities here, so what I'm gonna do is if you remember, we set a velocity at the beginning of this week, so I want to copy this velocity to these points, which they are exactly the same. So let's object merge our glass geo glass, and this should have a velocity. Yeah, there you go. So let's just copy it. As you remember, it's hard to see this velocity because it's packed primitive, so maybe sometimes bypassing these 2 times can work, but otherwise we can add only the points to this. And yeah, we have to copy the velocity to these points. There you go. And I checked the velocity, this is working fine, so let's go ahead and create a network. And as usual, we are gonna need the RVD packed objects, we need a rigid body solver, and we need some gravity. But this time, and this is the cool thing by doing this method, is that we don't need any constraint network, because we are driving the simulation, the active and the forming by this method. So this will go much faster. Let me just test this by setting this to active objects. Remember, we have to override the active and the forming. And let's grab the first input. Let's set it here. I would like to inherit point velocity. And as always, take a look at the pieces. Something like this, maybe less. Okay, and that's pretty much it. So let's give it a try. Maybe we can import our street light. Yeah, I want to import my street light, my simulation. So I'm gonna call this out prop sim and maybe connect it to the second input. I think this is already a packed primitive, so it has everything I need. So let's go here and let's call this glass. Let me see if I can use an animated object, static, with this prop sim. Let's call it prop. And I want this to be an animated second context geometry. I want this to be an animated static object. So let's see if this could work. Check the guide geometry. Set it as convex hull. Okay. Set this again. This. Okay, let's see if the forming and active attributes are working properly. I'm gonna hit play. It looks like it's breaking before I have the impact. Let me change this to the forming static object to see if it's No. Okay. Let me try something. Let's set a wrangle here. I call animated equals 1 and set this to override. Or maybe active. It's weird. This is simulation and this is the prop. So, okay. You know what? I think I'm gonna use a static object deforming because it's more reliable. So let's delete this and merge this thing with a ground plane and static object. Yeah, connect this here, here, and here. And I want to call wherever it's coming from the second input. So let's write our operator input path expression, jump up to levels, and I want the second input, so I need the 1, the forming geometry, and we can set this on as well to re-evaluate, and this will be the props. Okay. Let me see. We are using a bullet data, so we have to set the display flag on the merge. I don't want to see the ground plane, so I hide it. And again, set these two set of connected primitives. Yeah. Hopefully this will work, so let's hit play, frame by frame. I think this is working, yeah. Okay, now we should see these pieces near to this prop breaking. There you go. Okay. So we can play with the velocity, we can play with the substeps. Maybe we can also play with these sliders to set another length for the active attribute. We can play with the distance threshold. But as you can see, this is working. Of course, you need to spend more time here. We are saving all these edge classes, and the other ones are breaking apart. We can maybe tweak the velocity to see if we are using it. So I'm gonna call this attribute and multiply it by 10. Let me see now. Yeah, this is clearly working, so maybe we just have to multiply by 2 or by some random value. Okay. Now, let's follow by import this. And I want to grab the glass. And we should be sure, we should make an operation here. We have to be sure that we don't have neither active pieces equal to 0 and deforming to 0 at the same time, or active and deforming pieces with a value of 1. So what I will do is to create an attribute wrangle, and I will say if the attribute active equals to 1 and at the same time the attribute deforming equals to 1, just create a new delete, for example, and set it to 1. And same if this is 0. So I'm going to copy and paste this, and if these both attributes are 0, set it to 1. Let's give it some frames. And if this were 1, will mean that something is wrong. So a good way to, it's not happening now, but a good way to debug this will be to add a geometry wrangle, plug it here, and then you can say, you can copy the same conditional and say if this condition is true, then the forming will be 0. And if this condition is true with the zeros, then set active to 1. And this will help you to solve this issue in case you have it. Now we have one more step to do before switching to the high-res geometry. And of course, you should spend more time by tweaking the drag force of this, tweaking all the parameters you can get from the velocity and such. But what I want to do is to create, using this geometry, I want to get this geometry and to create a deforming static object out of this, because I want these parts of the car to interact with this glass, because otherwise we can get some pieces that are not behaving realistic. So I'm gonna teach you a very cool way to do this, and yeah, let's go to it. So basically the trick is to get the deformating object and the static one, merge it together and create a deformating static object to plug into the reusability solver. But as you can imagine, this has a lot of little pieces, a lot of open geometry, a lot of issues and problems that will lead this step to be super difficult. So I'm going to show you a cool technique, and let's start by calling the static object. Static should be, I guess, okay. And then we should call the deforming one. I think I want this. Let me see. Yeah, I'm gonna get this one, car body deform. Sorry, car body deform. Okay. So the first thing we have to do is to split these elements into the moving and static parts. And to do so, I need to somehow create an attribute that I will later on use to delete everything that is not moving or deforming. So let's first create a time shift, because I want this to be static all the time, and this here will have the moving parts. So what I will say is I'm gonna use the same method as you've seen before. I'm gonna grab the time shift to the first input, the moving geometry to the second. I'm gonna use the distance between these 2 points to generate a new delete attribute. So let's quickly set this as we had before. Is exactly the same wrangle, and if difference is bigger than some attribute, then I'm gonna call this attribute delete, and create a value here. And when I set some frames to it, there you go. We have some delete attribute here that we have to copy to the main deforming geometry. This is called delete. There you go. And let's blast this delete attribute. So delete equals 1, and this is points. Okay, so we'll have this deforming geometry here and the static one here. So let's start by the static one, and you'll see how efficient is this method. Instead of creating a convex decomposition out of these or BDBs, which will be impossible because we have open geometry, the trick is to create BDB from particles and then create a BDB out of these particles. So let's wrap and connect a scatter node here. Let's turn this off to have a faster computing, and I'm gonna go crazy with this number because I need something like this. Now, before applying the BDB from particles, be sure you have this value much lower, like 0.05, and let's set this to 0.02. Let's connect this. This might take a while or not. So let me see the resolution. We can go even more crazy. Okay, so let's lower this. Let me see if I can get lower point scale. Yeah, it should be fine. Next step, we can smooth this. We can BDB smooth this this output, and then in order to have the same shape as the geometry, we can use a BDB reshape SDF. I have to set this to erode, and maybe a little bit more, something like this. I can footprint this. No, this. Yeah, so we have something similar. And this will be our static geometry. So you should file cache this, but I don't have time for that, so I'm gonna use stash. And on the other hand, we can do the same here. So what I'm gonna do is to convex the composition this. This is not moving, so yeah, there you go. Let me check, because we don't have any geometry here because this is not moving, so it will be fine if we add a new time shift here and set this to some frame where we actually have the formations. Let me see. Now, actually, let me try something else. I'm not gonna use this convex decomposition. Instead, let's scatter some points here. I want to add these points to some frame. Yeah, this one. Or let me actually go back. Sorry for this. And let me try setting this to 15, for example. Okay. Okay, what I've done here is to offset the time where this is happening, and then I can have some geometry on the first frame. So what I would like to do is this is time dependent, so let's create now a time shift to the first frame, convex the composition this. There you go. I don't need this attribute. Let's set this lower. And now let's use a point deform. We want to deform this geometry using this one. So as always, I need a rest position. And let's see now. Yeah, there you go. Okay, let's convert this to BDB because we have to work with either everything geometry or everything BDB. So I'm gonna do the same as I did before. Maybe let's copy and paste this note here to have the same resolution. There you go. And in order to merge these BDBs, we have to use a BDB combine. So let's connect this, because otherwise you will have two different BDBs, as you can see here, surface and surface. But we want to merge them properly, so we have to use a BDB combine using a SDF union, as this is an SDF BDB. And there you go. Cool. Now, finally time to cache this. So let me see if I got some file cache around here. This one. Let's plug it here. Maybe call it source and no, forming static. And this time this type is a source. The element is a forming static car. And let's save this. I'm gonna pause the video. Hello again. So I've got this. Let me take a look. This is our deforming geometry. So let's plug this into the .network. So this will be our collision BDB, and BDB convert this to geometry, and this will be our collision geo. Maybe use a convert to have primitives. There you go. And you can pump up the adaptivity. Perfect. Let's call this geometry here, this side. I will use a static object. This is the static deforming car. So let's call the collision geo here, deforming, and remember we have to set this to volume sample, and let's call the collision BDB here, BDB. Okay, let's check the geometry. There you go. Maybe this is too much resolution, so we can maybe go here and hook a BDB resample, because I want to lower this 2,700,000 voxels. Let's use a voxel scale and multiply by 3 this, by 2, by 1.5. Yeah, that's better. Okay, let's go back here and I hit play. Of course, now it's taking much time, but we will have a more realistic simulation because the static object will interact with the glass. Cool. So let's import this. Check if we have anything wrong. Seems everything's right. So here you have your glass simulation. You can add this as out glass. And now we have all the elements combined. We have the glass, we have the car body deform, and we have the street light, and we have the static object. So as you can imagine, now it's time to use all the geometry to apply this effect if we are happy, and let's see what we get. Hello again. So I made this playbus with the final result using the complex geometry with all the polygons and with all the detail you can get from this kind of geometry. And as usual, changing this geometry, I realized that I fell into a few gotchas that fortunately weren't too hard to fix. So if I close this and I show you the new network, you will notice that I have several nodes painted as red, and those nodes contains the new information and the modifications I made. And so let's get started, for example, by first I want to show you that I used a lot of file cache to have checkpoints on each one of these steps, because once you change your geometry from the trimmed one to the complete geometry of the car by bypassing this blast, every time you are doing this, any one of these steps can take a long time to compute. So it would be clever to file cache, for example, after this top import where we have the street light. Then I think I make a new one here to cache the body deform of the whole car. Remember to bypass this blast as well. And of course I had to file cache the forming glass, because this takes a while to compute since it has a point deform, 2 solvers, and so on. Let me start showing you these gotchas by starting with the glass. No, this is actually not a gotcha, but I pump up the force total count to 5,000, and you will need another file cache here. Well, maybe you already had this one. So the first thing you have to tweak is this solver along with this attribute wrangle to set the forming an active object properly. If you dive inside the solver, the only change I made is to set this value to 0. I think this is what I had at the first try. You have to take the deforming attribute from the previous frame, and if this is 0, you have to replace it to 0. So then we have to add one more line here in this attribute wrangle, because until now we were only changing the active attribute. So now we have to add this deforming, because we want the deforming to be persistent too. And if you take a look now at the deforming values, now it's crashing, and you will see that everything in this all the geometry here has a deforming value of 1. So this is exactly what we got and what we want. The next gotcha could be on the dot network. This is actually not a gotcha, but some tricks that I made to speed up this process. For example, if you go to the RPD packed object regarding the glass, I changed the representation to box, as you can see here. So all of these can go faster. And also I change the bounce to 0. I don't want these particles to bounce. And as you can see in the playlist, they are kind of dying early, and I achieved this by setting a low sleeping time. I think that's pretty much it. And regarding the static deforming car, here, yeah, we really have a gotcha here, because if we don't specifically set this to volume collisions this time, it will think that this is a bullet geometry representation. So we have to set this to volume collisions. Let me jump back. And then what I did here is to file cache this glass simulation, not using the thread geometry from Top Network, but using points. Because let me show you what the difference between saving points and saving pack geometry. Here you have 50 frames of this simulation, and this is sized as almost 15 megabytes. But on the version 001, I saved the pack geometry, as you can see. And if I take a look at the size of this, you can see this is sized at 10 gigabytes. So you can easily see the difference. Let's set this to 002. And in order to transfer this animation to the main pieces, what we need is a transfer pieces node, as always, but careful here, because you don't want to transfer this animation to all of these pieces, but only to the active ones. And if you don't do this, you will see a weird animation, because the deforming pieces will still have a deformation on it, and this will lead us to a bad result. So firstly, you have to split the active from the not active, and these ones are the ones who have the deforming value of 1. So I want to keep these ones separately, and on the other hand, I have the actives. And these ones are the particles which I want to transfer the animation to. So I time shift this to the first frame, and I copy the active attribute. As you can see, we have an active animation here. Now I can delete everything but the active ones. And now it's time to use these transform pieces to transfer the animation to these static pieces. And this is what we do. As you can see, we are getting a nice result and realistic. So that's pretty much it. Then I merge all together in this render new node. And as you can see, we are having a nice deforming. We are having these little pieces of glass falling, and also this cool effect here with these little pieces of glass attached to the edge of this car. Okay, so that's all for this second module. You have plenty of work to do, and I hope you have enjoyed this week as much as I did. Remember, all the results we have achieved are just the tip of an iceberg of what you can get following all the tricks and techniques. And of course, don't forget to apply all of this knowledge on your own project, being creative, so each one of you can have different effects real. Yeah, that's all for now. So it's been a pleasure teaching you this module, and hopefully we'll see you again soon. Cheers!